Folks, we're back and we're going to talk more about some of the information that we can get from a mass spectrum. Notice that we haven't did a full-blown analysis of a mass spectrum yet. I'm just picking out little pieces and parts that we're going to eventually put all together at the very end. So in the previous video, we talked about the idea of an isotope and why M+1 peaks show up and why M+2 peaks show up. And that's really what our concern is about, M+1 and M+2. We said that with the M+1 peak, we can do a calculation that will allow us to determine the number of carbons, as long as we're talking about a hydrocarbon. And we said that an M+2 peak we can look at, those typically come from oxygen or bromine or chlorine, and depending upon the height of that M+2 peak, we'll be able to determine if things are present or not. So for instance, in the presence of bromine, that M+2 peak will be the same height as the M peak. And that will be a very good indicator that bromine is coming along with my compound. If it's 1/3 of the height, we said that was chlorine. And then if it's super tiny, then that's going to be due to typically oxygen that's going to be present in the molecule. All right, so something else that we can take away from the mass spectrum before we start a full-blown analysis. And this is something called the rule of 13. Now, 13, you should automatically think of the last video when we said that carbon can come to us in 12 or carbon can come to us in the form of 13. Carbon 12 is about 100%, 99. Carbon 13 is about 1% of the time, and that's why we had that multiplier in that equation. So let's say that we do not have information on an M+1 peak. Okay? The spectrum itself doesn't give us the abundance. We have no clue what the M+1 peak value is going to be. There is another option that we can use to determine the number of carbons that are in the system. And this is the rule of 13. So no M+1 peak basically means no abundance. We have no clue what the abundance is going to be. So this is another option that we can do. And it's pretty simple. What we do is we take the M peak, and the M peak will have a value that's assigned to it. So let's say the M peak is 100. That is the formula weight of the molecule that only lost an electron. It came through, it did not fragment up into pieces, it stayed together, and that weight is 100. That's the M to Z ratio. What we do in the rule of 13 is that we take that number and we divide by, guess what? 13. And what we would end up getting is 7.6923, something random and weird like that. Well, what can we take away from this calculation? The reason that we divide by 13 is that we overshoot it, because carbon can come to us in terms of 13. So we overshoot it to take that into account. We take 100 divided by 13 and we get 7.6923. All right, well, we kind of don't even round this off. Just look at the number. This number in front is 7. So this probably means that the compound has 7 carbons in total. Now we've got this remainder. Okay, well, this remainder doesn't mean anything. I'll show you a quicker way to do this than what a textbook would tell you to do, or literature would tell you to do with rule of 13. It's simpler than what it needs to be. Well, there are 7 carbons. So what I would do is I would go, okay, 7 times 12, because now we're going to use the real weight of carbon. It's 84. So if there's 7 carbons, this gives rise to an 84 formula weight at least. Well, we know that the total is going to be 100. So I'm going to take 100 and I'm going to subtract that from the 84 that came from the 7 carbons that I just determined. And that gives me 16. What does that 16 represent? Well, that 16 represents the number of hydrogens. Again, we're assuming hydrocarbon here. All carbon, all hydrogen. That's it, folks. That's the rule of 13. Again, go read a literature, go read a textbook. It's going to tell you to do all kinds of crazy crap that you don't need. This is it. This is all you need. You take the M-peak weight, divide by 13, and whatever number shows up here in the front, don't even round it. Whatever number shows up in front, that's the total number of carbons that you have. Then you go back and you do 7 times 12, which is the normal weight of carbon at that point. That gives us 84. Subtract that from the weight that they're giving you on the spectrum. That's 16, which will give you the number of hydrogens that's in existence. Now, notice at no point in time did we say how the carbons are hooked up. We do not know if it's a ring. We do not know if it's double bonds or triple bonds at this point. We do not know if there's pieces that are hanging off. That's not the purpose of it yet. I'm giving you baby steps at a time. Only thing I'm saying, 7 carbons in total. Who knows how they're hooked up? I don't really care at this point. And there's 16 hydrogens that's probably going to come along with this if it is a hydrocarbon. If it is a hydrocarbon. All right? Okay, so how does this rule of 13 come into play? Well, here's an example of what we just did. So this would be a mass spectrum that maybe would be provided, and I don't have any intensity values, no numbers that I can really go by. I've got to estimate them, but estimation is not going to get it close for me. I really have to have those numbers from the report, and let's say this report didn't have them. Well, here is my M-peak right there. That's 100. That's the example that we just did. So using the rule of 13, I would divide by 13. That would give me 7 carbons in total. 7 times 12 is 84, minus that from the 100 that they gave me, and this would be hydrogen number. So it looks like this would be a C7H16 at least. And sure enough, this is the mass spectrum. What's it the mass spectrum of? It's the mass spectrum of heptane, which is C7H16. So I was able to identify the condensed structure, at least of the molecule, just by using that 100. But again, it only works if it's a hydrocarbon. Now, let's look at another one. Here's a mass spec. Rule of 13, what's the formula of the hydrocarbon below? All right, so I see all of these lines. It looks like they get smaller and smaller and smaller as they go. It's a lot of information there to process, right? The base peak. Let's talk about the base peak. Right here's the base peak. I don't do squat with the base peak. I at least want to point it out, though, to tell you that is the most common fragment of this compound. Never forget it. I always like to review it. What's my M-peak? Well, this data over here to the side, it's going to kind of give me that information, because if I look, these are really tiny, and compared to this base peak, these are tiny, but you know, there's peaks out there, and that's a pretty dominant peak right in there, right? I mean, I can see that one. It's not really an isotope peak. Something like this would be an isotope peak, that little tiny one right there, or that little tiny one right here, or this little tiny one right there. You can't even hardly see them. Well, over here to the side, I see, look at this, 226, and the intensity is 2.1. Now, notice it just said 226. So there's 220, there's 222, 224, and 226 right there. Right beside of that one, there is a small little line. That's really happening at 227. If they gave me the abundance of that one, then I would be able to use that very first equation that we talked about. right? Where we took the percentage of the n plus 1 peak, divided it by 0.011 times the percentage of the m peak. But they don't. They give me 226, but that's it. They don't give me the abundance of the n plus 1. So I can't really use that equation. But I can use rule of 13 here, especially because they told me it was a hydrocarbon. So I'm going to take 226 and I'm going to divide by 13. All right, so I'm going to bring up the calculator. 226 divided by 13, and I hit enter. And I get 17.384. Who cares about that decimal? That doesn't mean anything. Chop it off. This 17 means that there's 17 carbons in existence. So C17 at least. All right, now where's all the extra weight coming from? If it's just hydrocarbon and that's it, then that means the rest of the weight is coming from the hydrogens. So I'm going to clear out my calculator and I'm going to say, listen, I've already determined there's 17 carbons here. So I'm going to multiply that by the normal weight of carbon, the average weight, which is 12, and this gives me 204. So I'm just going to write down that number down here below. It looks like the total weight is 226. All right, so 226 minus 204 gives me 22. So hydrogens, there's 22 of them. There you go. That's the condensed structure of this compound that was analyzed. And I only needed the M peak in order to do it. Again, we're assuming hydrocarbons, only carbon, only hydrogen. I don't really know how the molecule's structured at this point, but it gives me a very good place to start. I know there's 17 carbons. I know there's 22 hydrogens. How they're hooking up, I don't really care at this point. Which pieces are giving rise to the fragments that I see on the screen, don't really care about that either at this point. I'm just using the rule of 13 and that is it. But rule of 13 can be used and modified to give me more detail. So what does that mean? Well, that means it just doesn't have to deal with hydrocarbons. Hydrocarbons is how we like to start out to kind of prove the point, but you know, that's not the only thing that can be analyzed here. Rule of 13 can also be applied to non-hydrocarbon molecules, meaning other things can be involved like oxygens and nitrogens and sulfurs. We can do those. How do we do it? We just modify our last step. That's all that we do. All right, so how would I do this? Let's say that we have a compound that's composed of carbon, hydrogen, and oxygen. It tells me that at least. How would I know this information if it was an unknown? Well, I would do something that we would call an elemental analysis. You know, there is an instrument in the laboratory that we can inject samples on, and it will give me percentages of carbon and hydrogen and other things that it found that's present. So that way I can kind of make a better assumption of what we're using and what we have. So let's look at a mass spectrum. Carbon, hydrogen, and oxygen are present. What's the condensed formula? Use the rule of 13 to help figure it out. Okay, well this should be pretty simple. I'll just follow the rules of 13 like it was before. I look at this mass spectrum and I try to find the M peak. The M peak, well, I see a big one right here, but look, there's going to be one way out here at 73. It's kind of tiny, but this is the last one that they give me on this chart of data, and it is kind of dominant. I mean, we see 1.3% of the time. They don't give me any M plus 1 peaks, though. That would be like 74. right? So 73 is the highest number. 73 is the M peak, but I have no information on the M plus 1 or M plus 2 peaks or anything else. So the M peak is 73. So rule of 13 says take 73 and divide it by 13. All right, so let's bring up the calculator. I'm going to do 73 divided by 13, and I get 5.6153. So, chop it off. That tells me 5 carbons are in existence. So C5. All right, I'm going to bring the calculator back up, clear it out. And if I take 5 times 12, which is the normal weight of carbon, that gives me 60. Well, this says the total weight is 73. So I'm going to take 73 from 60, and I get a total of 13 hydrogens. So H13. Well, that's great. That's a hydrocarbon, though. That is not carbon, hydrogen, and oxygen. I have not factored in oxygen's weight at all. So this is what we do. If we want the oxygen weight, and we want to know the formula of it, and let's say they tell us there's one oxygen that's present, just one, I need to involve that oxygen somehow. Well, an oxygen weighs a total of 16. What I've done here is I've calculated the number of carbons and the number of hydrogens and just pretend it like it was a hydrocarbon, but I know that's not the case. So I've got to take away 16 so I can squeeze an oxygen into the structure. Well, how do I do that? Well, one carbon represents 12. That's 12 toward that 16 number. If I take away 4 hydrogens, well, 14 and 12 is 16. That will give me room to squeeze an oxygen in. So what I can do is I can add an oxygen. If it tells me there's one oxygen that's present, there we go. And then this 5, I had to take away 1 carbon to free up 12 formula weight. Will turn into a 4. And that 13, it's not going to be a 13 anymore. I had to take away 4 from that. That way I can free up that 16 in total for that oxygen. So what was an H13, if I had to take 4 away, it's now going to be an H9. There you go. There is my structure for this compound. If they tell me 1 oxygen is present, this is what I would do. If it tells me 2 oxygens are present, I'll just do it again. Take away another carbon, take it to 3. Take away 4 more hydrogens, take it to 5. And then slap on another oxygen to the molecule. That's the only thing. You're trading off the weight. That's it. You're starting off with carbon and hydrogen only. You're adding maybe an oxygen. It works with nitrogen and stuff too. It doesn't really matter what it is. Nitrogens weigh 14. So you would have to take away 1 carbon in this case to free up 12, and you would have to take away 2 more hydrogens to free up a total of 14 weight. Take away a carbon, take away 2 hydrogens, slap a nitrogen onto the molecule, and you got it. That's going to be the power of the rule of 13. And that's how we modify it, just in case we do not have a hydrocarbon that's in the system. So here are some more example problems, and we're going to work through these 3 just so you can feel more comfortable about what we're doing. It says, draw the possible structures for an ester that has a molecular ion with an M to Z of 74. All right, so the first thing I'm going to do is take 74 divided by 13. So I'll bring this up. 74 divided by 13 is 5.69. So this means there's 5 carbons in play. All right, so I'll take 5 times 12, the weight of carbon, that's 60. I'm going to subtract 74 from that number, and I'll get 14 hydrogens. So C5H14. Now, the problem says an ester. What is an ester? Well, an ester is a carbon double bonded to an O that is on another oxygen. So here's the problem. I need to free up 2 places for oxygen. All right, well, I'm going to take away 1 carbon, C4. I'm going to take away 4 hydrogens to give me a freed up 16 in total. So that's 10 with an O group. But this requires another oxygen here, right? So now I'm going to have to free up another 16. So I'll go to 3. I'll take away another 4 right there, which will give me a 6, and that gives me an O2. Now, I'm going to quickly calculate this over to the side. 12 times 3 plus 1 times 6 plus 16 times 2. That gives me 74. It matches. C3H6O2. Now, how is that actually adding up? How is that linked up? I'm not really concerned with that right now. The only thing that I'm after is the condensed structure of the molecule that I ran. And look at what I just did, people. I knew the functional group. How can I get this functional group? That's easy. Do an infrared of it. It tells me this is an ester. I run that on a mass spectrometer. I use the M-peak. That's it. Just the M-peak alone. And I'm able to determine that this molecule has 3 carbons, 6 hydrogens, and 2 oxygens in play. Again, that's the power of the mass spec. And when you couple that with an infrared, everything that you need to know about the molecules at the source of your fingertips with just a bunch of lines and squibbles. Kind of amazing when you sit back and think about it. Let's look at a second one. A compound that contains carbon, hydrogen, and 2 oxygens that has a molecular ion with an M to Z of 102. All right, I don't really know the functional group here, so I'm just going to take 102 and I'm going to divide it by 13. So 102 divided by 13, that gives me 7, right? I told you, look at the whole number. Don't round it off. So I've got a total of 7 carbons. So 7 times 12, which is the normal weight of carbon, equals 84. The total is 102. So that difference is 18. So this gives me C7H18. Well, I need to squeeze in an oxygen. But in order to do that, I need to free up 16 formula weight. Well, if I take 1 from carbon, that frees up 12. And I take away 4 from the hydrogen, that frees up 4 more, which will give me 16. So there's my number 1. And then I do this again because it says 2 oxygens. So I'll take away another carbon. So it gives me 5. I'll take away 4 more hydrogens to give me 10. And this will give me another 16 freed up spot that I can squeeze another oxygen into. So the condensed structure is C5H10O2. Again, the only thing I needed to know was what was there and what's the formula weight. That's it. The rule of 13 will be very powerful in helping me determine the condensed structure of these molecules. Again, carbon weighs 12, hydrogen weighs 1. So I need 1 carbon and I need to take away 4 hydrogens in order to take away a 16 in total. That way, when I add my oxygen, which weighs 16, it evens out. That's why we're doing that. Finally, the last one, an amide that has a molecular ion with an M to Z of 115. All right, so who cares about the functional group right now? We're just going to do rule of 13 as it's written. So I'll take 115 divided by 13. That gives me 8. So 8 carbons in total. So 12 times 8 is 96. Well, it weighs 115, so that gives me 19. So H19, that's where I'm going to start. Now, what is an amide? Well, an amide is a carbon double bonded to an oxygen that has a NH2 group on it. That's your amide. So you need to make room for an oxygen and you need to make room for a nitrogen. Okay, no big deal. I'm going to make room for my oxygen first. So if I have carbon and hydrogen, I need to squeeze in an O. But in order to do that, I need to free up 16. So I'll take a carbon away, bring it down to 7. That frees up 12. And I take away 4 hydrogens here. So that goes to 15. And that allows me to free up 16 formula weights so oxygen can be squeezed in. C7, H15, O. Now the problem is that I have to make room for a nitrogen as well. Okay, no big deal. Nitrogen weighs 14. So I'll take away 1 more carbon, which brings us to 6. That frees up 12. And I need a space for 2 more. So instead of 15 hydrogens, I'll go to 13 hydrogens. All right, so that gives me freed up of 14, which allows me to bring in my nitrogen. And now I have the condensed structure, C6H13ON. All right, so over here to the side, I'm going to add up all the weights. 12 times 6 plus 13 times 1 plus 16 from the O and 14 from the N, which gives me 115 in total. And that's exactly what the question says, my M to Z of 115. So again, condensed structure, that's all that I'm after. I have no clue how these are linked, but no big deal. We'll talk about that in another video.